A polyatomic ion consists of several atoms, typically of elements other than metals that are connected by covalent bonds. Lewis dot structures for polyatomic ions are drawn similarly to the way they are drawn for molecules. An important difference, however, is that polyatomic ions are not electrically neutral. Therefore, the number of electrons that are available for bonding in polyatomic ions isn't simply the total number of valence electrons that are provided by all atoms that form the ion. Rather, for a polyatomic cation, the number of electrons is smaller by the charge of the cation, and for a polyatomic anion, the number of electrons is larger by the charge of the anion. Consider the example of the ammonium cation, NH4+. In this polyatomic cation, the nitrogen atom supplies 5 valence electrons, and each of the 4 hydrogen atoms supplies 1 valence electron, for a total of 9 electrons. 1 electron is removed from the cation to give it its plus charge. Therefore, the number of electrons that are available for bonding is 9 minus 1, or 8. These 8 electrons are used to form 4 covalent single bonds, one between the nitrogen atom and each of the hydrogen atoms. In this structure, the nitrogen atom has access to 8 electrons that form the 4 covalent bonds, an octet. Each hydrogen atom has access to 2 electrons that form the covalent bond between that hydrogen atom and the central nitrogen atom, a duet. The Lewis dot structure of a polyatomic ion is enclosed in square brackets, with the charge of the ion indicated as a superscript. Now consider the example of the sulfate anion, SO4 2-. In this polyatomic anion, the sulfur atom supplies 6 valence electrons, and each of the 4 oxygen atoms also supply 6 valence electrons, for a total of 6 plus 4 times 6, 30 electrons. An extra 2 electrons are added to the polyatomic anion to give it its 2- charge. Therefore, the number of electrons that are available for bonding is 30 plus 2, or 32. The central sulfur atom forms covalent single bonds with each of the 4 oxygen atoms, resulting in an octet for the sulfur atom and access to 2 electrons for each of the oxygen atoms. To give an octet to each of the oxygen atoms, we must add 3 lone pairs to each of these atoms. At this point, we have used up all 32 available electrons. 8 are used to form bonds, and the rest reside on oxygen atoms as lone electron pairs. The Lewis dot structure of a polyatomic ion is enclosed in square brackets, with the charge of the ion indicated as the superscript. A natural question to ask is where the extra electrons in polyatomic ions that give them a negative charge come from, and where 2 electrons that are removed from polyatomic cations go to give them a positive charge. To answer this question, we should remind ourselves that polyatomic ions occur as constituent parts of ionic compounds or acids. For instance, in calcium sulfate, the 2 electrons that give the sulfate ion its charge 2- are donated by a calcium atom that thus forms the calcium 2+ cation. To write the Lewis dot structure of an ionic compound that contains a polyatomic ion, first write the Lewis dot structure of the polyatomic ion, as you would for a molecular compound. Then use this ion in the Lewis dot structure of the compound as you would normally do for an ionic compound, indicating the charges of all ions that form it. For instance, the loose dot structure of calcium sulfate is shown on the slide. In some cases, both ions that form an ionic compound may be polyatomic. An example of such a compound is ammonium hydroxide. To draw its loose dot structure, we first draw the loose dot structures of the ammonium cation and the hydroxide anion, then put the two ions together to form the ionic compound.